Right, so this is a particle and wedge system now. The next section on the handout, or the next type of accelerations actually, and it's the next part of the handout. So, a particle and wedge system, what is it? So what you have is, normally it's a right angled wedge, but not always. But for this one, a right angled wedge. And sitting on it, you have a particle of mass. This particular case, it's called mass m, and we're told that this wedge is 3m. And this wedge has an angle, this sloped surface is at alpha to the horizontal. So it's a right angular triangular block of material with a smooth sloped face. This is always smooth for us in leave insert. A particle is in contact with it, so this particle is in contact with the smooth surface, and the wedge is supported by a horizontal surface. So we're sitting on something, a table or some horizontal surface. And when the system is released from rest, the particle begins to accelerate down the inclined face of the wedge. So it acts down like that with an acceleration of a, and the wedge has a consequent horizontal acceleration to the right. So the wedge's acceleration I'm going to call b. This is different to what the systems we did last year, which were fixed planes, where the plane didn't move. You had a particle on the plane, but the plane didn't move. Now we have a wedge that moves. So what you do is you have to consider them both separately. So we take the wedge and we take the particle. So the particle is sitting on the wedge. We draw all the forces on the particle and all the forces on the wedge. So this has a weight force which acts down mg. It has a reaction to the surface, which I'm going to call r. Because the acceleration of the wedge is along that sloped plane, you have to resolve the weight force into its two components. So I'm going to draw a right angle triangle around the weight, and I'm going to break this into its two components. Now remember, it's the same as what we did last year for weight on a plane. Remember, this will come down here, that'll be a right angle, that'll be angle dot. This, of course, this red line makes an angle 90 degrees with the plane, or it's perpendicular to the plane, so this is at 90 degrees to that plane, so this has to be angle alpha. Which means that this, my weight force here becomes mg, this component is the cos alpha, because it's adjacent, and this one is sine alpha. I'm going to cross that mg out then, he's finished, not interested in him. So I've got three forces that I am interested in, this black r and these two red ones. Now, then I go over to the wedge and have a look at the forces I'm interested in here. Of course, I've got a 3 mg weight force, which I want. It is on a surface, so though there will be a reaction to the plane, I might call that n. And then the particle, so the reaction here to the particle is from the wedge, and the same reaction will act towards the wedge, like that. So this is the direction of the acceleration of the wedge, horizontal to the plane, which means I need to resolve that r force. This is the r coming in. I need to break it into its two components, parallel and perpendicular to the surface of that table or whatever it's on. So this will be the perpendicular one, and this of course will be the parallel one. If I were to continue that and make that a nice right angle triangle like that, this is a right angle. This angle here is alpha. This is angle dot. So this angle here must be 90 minus dot, which makes this angle there alpha. I then have my two red lines. This is opposite side, so this is r sine alpha, and this one here is r cos alpha. I'll write it there, r cos alpha. And once I've resolved the r, I no longer want that, so that's gone. So once you have all of your diagrams up and your forces resolved, what you then do is you draw up a series of equations, as we did before. Now, we have to consider, because we have two things going on, we have parallel forces and perpendicular forces. We must consider both. So this is parallel forces parallel to the plane of motion, and we have perpendicular to the plane of motion. Perpendicular to the plane of motion. That should be PLNE, perpendicular. Okay, so we're going to write up the equations that we're interested in. So we're going to write up equations for the particle and for the wedge, parallel to the plane and perpendicular to the plane. So we're looking at the F nets equals ma. So we're going to write Newton's second law equation for the particle under two conditions. So here's your particle's forces. There's only one of them now which is parallel to the plane, and that's mg sine alpha. So F nets equals ma, so the F nets is just mg sine alpha, there's only one, is equal to ma, m, times the acceleration parallel to the plane. You come up here to this diagram and you look at the accelerations parallel to the plane. So there are two, there's the blue A and there's the red B cos alpha, but they're going in two different directions. And the particle is moving down the plane, so that's going to be A is the positive one minus B cos alpha because it's acting in the opposite direction. Then I move over perpendicular to the plane. Perpendicular to the plane is the particle has two forces, mg cos alpha and r. Of course, the particle is staying on the surface, so the mg cos alpha minus r, because this isn't, the particle is not leaving the surface, equals m into the accelerations perpendicular to the surface. So back up to this diagram here, there's only one acceleration perpendicular to the surface, and that's mb sine alpha. Now for the wedge, we have a look, here's my wedge diagram. Look at the forces parallel to the plane. There's only one, r sine alpha, is equal to m, which in this case is 3m, and the force, the acceleration parallel to the plane, it's just b. There's only one acceleration parallel to the plane here for the wedge. And then I look perpendicular to the plane. I've got three forces perpendicular to the plane, two acting down, one up. And the wedge is staying on the surface there of that table. So that's going to be 3mg plus r cos alpha minus n is equal to 3m multiplied by the acceleration perpendicular to the plane. There is none. There is no acceleration perpendicular to the plane here for the wedge. The wedge's acceleration only acts in the I direction. There's no j component, so that's just 0. So these would be my four equations, and that's where I would begin my question. So I'd have to start the question. So let's apply that now to an example that's given on the handout. It says a particle is in contact with the smooth sloped face. Sorry, no, I'll just get the question, be handy. So this is, you're taking that situation that I've just drawn and you are talking about a particle of mass 1 kilo. So here we have a wedge with the particle. It has a mass of 1 kilo acting down, call that mg. There is a reaction to the surface, obviously that's called r. It's sitting on a wedge, so here's my wedge. Draw nice big diagrams in pencil. The mass of the wedge is 5 kilos, so that's 5g acting down. There's a normal reaction to the surface that it's on that table. I'm going to call that n. And of course then there is an r acting in, an opposite and equal reaction force acting in. Okay, so they're my forces. That's the first diagram, the unresolved forces. And then you're going to draw a second set of diagrams with resolved forces. And I'm going to skip that and I'm just going to go straight to resolving these. This, it says, tells me in the question that this wedge is at 30 degrees to the horizontal. So I'm going to resolve all the forces. Resolve the weight force. So of course this becomes mg cos alpha, which is cos 30, and this is mg sine alpha, mg sine 30. Then I come over here. I'm going to break this into its two components, of course, the R force. This, remember, is the R force acting in. Remember what we did in this in the previous diagram up there. We're going to break it into its two components. So remember, this is at 30 degrees in this case. This is right angle, this is dot. This is 90 minus dot, which means this is 30. This, of course, is your right angle. So this one over here will be the opposite to 30. So this will become r sine 30. And this one, of course, is the adjacent. So it's r cos 30. And once I have that, I don't want the r anymore. I break it, I cross it out, and I'm going to cross out that mg as well. Now, I'm going to use those diagrams then to draw up an equation for myself. Draw up a series of equations for myself. So, I'm going to look parallel. I want the forces parallel to the plane of motion, and I want the forces perpendicular to the plane of motion. So 2 equations for each one. So 2 equations for the particle, 2 equations for the wedge. Now the question says, show that the wedge has a horizontal acceleration of g root 3 over 21. Okay, so that's my particle diagram, that's my wedge diagram. The other thing I have to draw, remember, is the acceleration diagram. So here is my acceleration, and I'm saying obviously the particle will move down the wedge with an acceleration a, and the wedge will move to the right with an acceleration b. So this is my particle, this is the acceleration a moving down. I'm going to break my b acceleration into its 2 components. So let me just get that black pen, where is it? There it is. So this is the b acceleration. This is the a acceleration, and remember that is on the surface here of the wedge. So I'm going to take the b, I'm going to break it into its 2 components. I'm going to draw a right angle triangle around it, perpendicular to the plane and parallel to the plane. And remember that this angle down here is 30 degrees, which is 30 over there as well then, by the corresponding angle. And if this is at right angles, then this is going to be, we'll say 90 minus 30, which if I call that dot, that's going to be 60 in this case, but anyway. And this is a right angle, which means this angle over here is my 30 degree angle over there. So this one is the adjacent, so this becomes b cos 30. And of course, this one is the opposite, so this one is b sine 30. So that's my acceleration diagram, my particle diagram, and my wedge diagram. So I've got pour done. So once I have pour done, now I'm going to write the equations. So the particle parallel to the plane, that's this one, mg sine 30. So is equal to m into, now the acceleration parallel to the plane. So here's my accelerations for the particle. There's parallel to the plane, a and b cos 30, and of course they're in 2 different directions. So it's a minus b cos 30. A is down, b's up. This one over here, perpendicular to the plane. These are that there's only one weight force perpendicular to, there's 2, sorry, there's one acting down and one up. So this becomes mg cos 30 minus r equals m, and in this case actually the m was 1 kilo, wasn't it? So I was told in the question the m was 1 kilo. I'll remember that when I'm continuing through the question. So this becomes m into, now there's only one perpendicular acceleration, and it's this one, which is the b sine 30. Then I look at the wedge. The particles parallel to, or the force is parallel to the plane. There's only one, it's r sine 30, equals ma. The m is 5. The acceleration parallel to the plane is just b. Now I look at the perpendicular to the plane for the wedge. I've got 3 forces, 2 acting down, 1 acting up. So that's 5g minus r cos 30, sorry, plus r cos 30, because it's both acting down, minus n is equal to ma 5 times. Now the acceleration perpendicular to the table, remember there's only B acting in the I direction. There is no J component, so that's 0. The particle, the wedge is not moving up and down from the table. So I'm going to use these 4 equations to find the acceleration of the wedge. So this becomes, remember the m's are 1 for this particular question, so those m's will cancel anyway. So that will give me g sine 30. Sine 30 is a half, so a half g is equal to a minus b cos 30. Cos 30 is root 3 over 2. This equation here is r times sine 30, of course, which is a half, is equal to 5b. So this will give me something for r. R is equal to 10b. Okay, now I'm going to put this equation, or this r, into this equation here. So this will become mg, this one here will become mg cos 30, that's root 3 over 2, and m, remember we said was 1 kilo, so that's just 1. So root 3 over 2 times g minus r is equal to m, which is 1, b sine 30 will give me sine of 30, remember, is a half b. So this becomes root 3 over 2g minus r is 10b equals a half b. So this will be root 3 over 2g is equal to 10 and a half, that's b, 10 and a half b, which of course is 21 over 2. So that means b is equal to root 3 over 21g. And that's an acceleration, so it's meters per second squared. And that's what I was asked to prove. I was asked to show that the acceleration of the wedge was that.